totally go for S first. Because I don't want to go plugging nastiness into that. Like, that's just awful. So instead, let's just go for S. S is called the semi-perimeter, which, I mean, kind of makes sense. You add up all the sides and divide by 2, because semi is half. So when we go ahead, plus 53 plus 72 in half. Oh, no one needs to borrow my calculator today, so let me go grab it. Although some of you might be able to mental math that, because that's 96 plus 72, 98 plus 70, 168 cut in half, 84. Anybody beat me there? I'm not always perfect, just double check. No mental mathers beat me there? Jason's nodding his head. Did you mental math it, though?
Oh, for this, I didn't even do that example. I just went straight to the homework.
Oh, no, you're okay. I meant right now, just double checking me. Oh. Any mental mathers doing
Sounds
it?
Right.
I can make really bad things sound right. Really wrong things. Although chapel yesterday, bad things can sound right too. Anyway. They can sound really good too. And they do. Temptation. Okay. 84. I double checked it. I'm right. Some of you were trying to help like very quietly. Be louder. Okay, now what?
Oh, yeah.
There you go. Now what? Yeah. So how do we plug in? We use 84 a lot. True?
Yeah.
Now some of you were like literally, I would just, if I were you and you're plugging it into your calculator, wouldn't it save you time just to, put it all in at once? 84 minus 43. Now some of you might want to do the mental math, but just heads up, you're not going to be able to mental math multiply 3 two-digit numbers. Like, I don't know. I would just say plug it in. That way you don't make a silly mistake and then mess up your whole problem. 84 minus what, 72? Because in years past, cool, that's 41, and then that one is going to be 31, and that one's going to be 8. But I'm not going to do that in my head, so whatever. Just throw it in your calculator. Handle it. Life lessons for that too. Sometimes we try to just control and do everything ourselves. Explain bad things that happen. God's shoulders are big enough. Just throw it on him. Perfect. That's what I got too. You guys backing this up? That is a large area. But it's also a large triangle if you think about it. It's like a plot of land sort of triangle. 1,130, right? Like meters? There's a meter stick. A meter stick is kind of like a yardstick.
That's like the average house property.
Really? I don't measure things in meters. It could be like square feet.
Oh, no. I guess you're right.
Right? I was thinking square feet. Well, it wouldn't be an average house. That's a kind of small, if that was feet. But it'd be like the size of my condo. 1131.89.
Yes.
Although I guess in the valley maybe. Some places are a little bit smaller. Okay. Shoop. You'd have to do meters to feet, but meters are longer than feet. Aren't meters?
It's like 3 points.
A meter stick. Is it like a yard? Yeah. Yeah, a meter stick is like a yardstick-ish, and it's 3-ish. Okay, that makes sense. Yeah, it's pretty big. Okay, so Heron's formula. Some people call it Hero's formula. I mean, it could be your hero, but technically the guy's name was Heron. But anyway, Heron? I guess we call it Heron. I don't know. I think I call it Heron just because I have seen it as Hero's formula, and so in my head it's just Heron, whatever. Call it whatever you want. I don't know the dude. He's dead for a while, so not sure how to go ask him. Coming back. I could go, maybe we could figure it out from that. Homework number 39, section 6.2. Let's go grade. And stop going off on tangents. Oh, which is so mathematical. Anyway. I love your guys' comebacks. They crack me up. I only hear like half of them. Because you guys do it in like a really small, subtle way. Okay. Number 2 is the law of sines. Number 10, you guys have a lot of stuff to grade again. So let me give you a little bit of time to digest and check. You know, sometimes when I'm supposed to be doing something and someone's talking over it, I just get confused and distracted. Let me look up Huron and see where he was from my college history of math class book. Yeah, I got mocked for this one when I was doing homework. You have a math history class? Yep. A condensed version. I don't know where the full version is. I'm not sure if anyone ever wanted to write it. There we go. Just kidding, it doesn't actually say condensed, but there's more to math than that. That's why I said condensed. But it's not literally a condensed version. Good question. Ah, Alexandria. He was Egyptian. I'm not sure if that helps us at all as far as how to say it. We'll go ask Melody. Huron's formula. Can I scroll down? You guys good? Cool. Let's finish off 36. Ooh, it was found in the book of Lemmus, which has been lost. It did not survive in the original Greek, but an Arabic translation was found and then translated into the Latin. Had to do with the cattle problem. That sounds exciting. The number of bulls and cows of each 4 colors. There are 4 different colors of cows and bulls. Go figure. The Pell equation. There's a lot going on. The vector dude. I don't know the vector dude. Should I know the vector dude? Can I scroll down? Do you guys like this homework better than 6.1? 6.1 was nice up until the ambiguous and then the weird like dangling sides and trying to figure out 1 or 2 or none, right? Oh yeah, bearing. Yeah. And then the Leaning Tower of Pisa. Ugh. I think 6.2 was supposed to be easier. Vectors. Vector analysis, space vectors. Let's just go normal vectors. 584. Grossman? Oh, Hamilton. Yeah, good job. Not that Hamilton, but good Broadway. Haven't seen it. Good music. Although sad ending. But if you guys took U.S. history, it's a sad ending. Oh, this is all in Hamilton. To figure out about Hamilton, I have to go way back. And then it's De Morgan. Hamilton had to do with vectors. He was at Cambridge. Not that Hamilton. He was following after Newton. We all do it, just not like that. Hamilton treated quaternions as vectors and essentially showed they form a linear vector space over the real number field. Yeah, he did a lot of stuff with vectors. Matthew, if you ever want it, there it is. 38. 38. It was just plugging into Hero's formula and getting Huron's formula. Anyway, 399.04. Number 56 was a bit brutal. Why was 56 a bit brutal? You were missing the little guy in here. You weren't missing him. Oh. Because you had to match the 7 with his angle theta, and then you had the x in here that was like a squared. There was a quadratic. So what did they do? The quadratic formula. Oof. X equals negative b plus or minus square root b squared minus 4ac. And so their b was the cosine dude. Now they went ahead and rewrote it because they were able to like simplify the radical and oh no, they didn't simplify the radical, they just left it. But 66 should have been easy in the sense of anytime you have more than one side, usually law of cosines. Anytime you have more than one angle, usually law of sines. The one exception is the ambiguous case. The ambiguous case, long story short, if you don't like the quadratic formula, the best way to do the ambiguous case is law of sines, the 180 minus sine inverse trick. It's the best, easiest way to deal with the ambiguous SSA or ASS case. Let me zoom in really quickly. I know some of you guys are checking out that quadratic formula nonsense, but it's not nonsense. It's actually how to solve. and number 56. So you had to put the 7 because it was the opposite side from the theta. There was only one way, like you couldn't put the 1.5 or put the x, sadly. So the x ended up getting stuck inside the law of cosines. So what they did is they went ahead and multiplied everything out, moved it all to one side, and they said, ooh, well, we have a quadratic where a is 1, b is everything besides x, so negative 3 cosine theta, and c is negative 46.75. And then they sang the song, x equals negative b plus or minus square root b squared minus 4ac all over 2a. And then they said, let's do that and make it look nicer, and let's do that and make it look nicer, and then let's take the divided by 2 and pull it out here and make it look nicer. Man, vanity, thy name is. Math key makers. They simplified it to make it look nicer. Then they threw it in their calculator, and then they said, hey, once it's in our calculator, we can just find the max. Wait, how do you find the maximum in your calculator? Second, trace. So once they got this in their grapher, then they went ahead and said, I can find the max, and the max ended up being 8.5. All right, cool kids, I have the homework ready. Anything on the odds or the evens? I'm just leaving this up for a bit because I know it was a lot of math with the quadratic formula. 51. Anything else? 20. Another one? Okay, keep looking. Wesley. Oh, sorry, you're just, my bad. 51 and 25. Okay, cool. Let's start with 25 because it's earlier, and then we'll go to 51 because it's later. So 25, you're trying to fill in stuff of a parallelogram. Whew. All right. Complete the table, so fill in the missing stuff. By solving the parallelogram, the lengths of the diagonals are given by C and D. So what can we fill in? We know that A is equal to 5, so I'm just going to put 5 right there. We know that B is equal to 8, we'll put that right there. C and D, no say. And then theta is 45 degrees. Huh. I think I see a side angle this parallelogram. You guys agree? Just solve our triangle. When we solve our triangle, won't we get D? Yeah. Sweet. So we could go ahead and do, wouldn't it be B squared because we have his opposite cosine of 45? And then the rest of the formula is kind of like Pythagorean. So 5 squared plus 8 squared, but then you have that weird 2 times with a minus. Haha. Okay. Oh, let me erase. Let me erase. I thought I saw it, but maybe I didn't. Nope, it's the whole thing. See? It's the whole thing. Of a parallelogram? No. Parallelograms are rectangles, yeah. Parallelograms, nope. Because you have obtuse angles and you have acute angles. So yeah, this one's just 45. Rectangles are parallelograms, true. So it could be 90. That's as far as the terminology, Matthew, you're right. But parallelograms in its loosest sense include skewed angles. Is that a better way of saying it? So we have no guarantees that's a right angle. There you go. So then when they say 45, cool. They just drew a general picture, and if you guys notice, there were tons of problems underneath, so they made thetas lots of different things. They just drew us like a basic one. So then when you guys solved, what did you get for D by square rooting both sides? I actually need it. 0.65? 69. Good. Okay. Once we have D, 5.69, now who do we have to go looking for? Ugh. So what do we know about parallelograms? What's this side going to be? What's that side going to be? Even if you're skewed, it's still opposite sides are congruent. Do we know anything else? Other side's 45. What do 4 angles in a parallelogram have to add up to? Which one? 360. Think, if it's a rectangle, wouldn't there be 4 90s? 4 times 9 is 36, 360. Or you can think 2 triangles whose angles both add up to 180. However you think about it, I need 360 total. So couldn't I do for my angles 360 minus 45 and 45 is 90. How many degrees are still chilling out there? 270, and I need, you guys realize those are congruent. If these are congruent also, I just need to cut this in half to find my other angle. So I know my other angle is 135. Jason. Phi. Phi, fo, fum. I smell the blood of an Englishman. Okay, so. Did we figure out that was Jack and the Beanstalk or Gulliver's Travels? Jack and the Beanstalk. Oh, because he got up in the midnight. Okay. Long story short, why am I trying to find 135?
So you can make another triangle.
So I can make another triangle for C. So I can say, aha, 8, 5, 135. It's time to go find C. So to go find C, nice thing is, basically the same idea, except instead of, yeah. Oh. What'd you guys end up getting? Is that good? We had to play around with parallelograms and angles and opposite sides and triangles and a parallelogram and all that jazz. Good question. 51?
Yes.
Oh, that's okay. Hey, my book's working today. Thank you, book. 51. It's a bearing problem. All right, you had bearing come back in the section 2. It's okay. If you guys notice in section 6.3, vectors were getting like super practical as far as like physics and motion and distance, and bearings are kind of practical. Minneapolis. Hey, geography lesson. Minneapolis is 165 millimeters. What's it talking about? On the map. Due west of, right? Like, not millimeters. Due west of Albany, Phoenix. 200, Albany, yeah. It's like Albany, Phoenix. Never heard of that one before. Of Albany, New York. Phoenix is 216 millimeters from Minneapolis. Phoenix is okay. Pretty short. Of Minneapolis from Phoenix. Okay, with bearings. Remember how I said yesterday you're in the ocean, you're a pirate way back when, and you're trying to figure out where north, south, east, west is, and your compass is falling overboard? I didn't say all that, but that's okay. How do you find your bearings? You ever heard that phrase before? Get your bearings? The sun, problem with the sun is it moves. Sun, and then you know what time it is, but their compass fell overboard. Where's their clock going to be? Anyway. They might have a sundial. And it's nighttime. The North Star. The moon moves too. Anyway, the North Star. Okay. Long story short, bearings need the North Star, need north. And then you just say, where's north? Okay. Whew, there he is. It's a cloudy night. We're just not going to talk about it. So, North Star. And then you move clockwise around in an angle. If they say the bearing of Minneapolis from Phoenix, whose north are we using? Minneapolis or Phoenix? Why Phoenix? From. Who's the origin? Who's the starting point? Phoenix is. Phoenix, someone's in Phoenix wanting to get to Minneapolis and saying, okay, from Phoenix, how do I get to Minneapolis? So we're going to Phoenix's north. Does that kind of make sense? From Phoenix. You're in Phoenix trying to get to Minneapolis. From Phoenix, they want to know this angle. But it's not in my triangle. Why am I going to draw a line here? Because what did it say about Minneapolis to Albany? Due
East.
Technically west. But yeah, you're right. It's the east-west line, right? What do we know about these two lines?
Parallel.
What do we know about angles? Same side interior angles of parallel lines. They add up to equal 180. Is he in the triangle? Yes. Law of cosine. Find him, let's call him A just because. To find him, yeah. And I can do the other two sides. Double check my work. It's going to be b squared c squared, right?
Yeah.
Minus a squared. Uh-oh, I just covered him up. Was that 216? Yeah, there it is. Minus 368 squared all over 2 times 165 times 216. I can find angle A by doing cosine inverse of the bleh. And then I can use angle A to figure out who this guy is down here, angle B. And then what does angle B and that guy need to add up to? 90. I know, right? Whew. So there's a lot of stuff going on. But long story short, I need to use law of cosines to figure out that A guy, the angle between the Phoenix to Minneapolis line and the Minneapolis to Albany line. So I'm throwing that in really fast just because maybe I can check you or you can check me. Plus 216 squared minus 368 squared all over 2 times 165 times 216. Is anybody backing me up? Awkward. Awkward. Well, either way I need A, don't I, Joe? Yeah. Okay. I need to get in degree mode. I did not get in degree mode. I just put my cursor, enter. Now I'm in degree mode. Anybody ever do that mistake? 149 point. So that B is going to be 180 minus. Joe, it's ultimately what ends up happening, right? Yeah. But at the same time, I'm just trying to show the math as to why. Is that okay? So then to find theta, the bearing, I say, okay, 90 minus B, which will end up being the same thing as this guy minus 90. 59.70. And we have A. Hey, it's still easier than the Leaning Tower of Pisa problem. What's B say? Who's north?
Phoenix is north.
Still Phoenix is north. Good. So now it's saying, okay, what if you're not going to Minneapolis? What if you're going to Albany? Well, hold on. I still have my A, I still have my B, but I'm just going ahead and trying to figure out. So from Albany, wait, isn't part of that theta still? Yeah. What do I need? Oh, let's just solve law of cosines again. Because for this one, I'm just going to go ahead and take theta minus C. Who's C? That little guy. Okay. So now how do I set up? I need cosine of C to equal the other two guys. So 368 squared plus 216 squared minus 165 squared all over 2 times 368 times 216. Cosine inverse both sides. You guys double checking me? I'm going to go steal my other cosine inverse and just switch the numbers. So 216 is fine. Oh, 165 isn't. 368. Got him. Now let's go check and change him. 165 goes in the minus spot, and 368 goes in the plus spot. Yeah. 1307?
Yeah.
Now all we have to do minus him. So bearing, got it, minus him, 46.63. What? Oh, what happened? Here. But it turns out
I get that.
you get it. It just wasn't working. Okay. I didn't know if plugging in. Well, Salma, what I do is I go up and I steal the other cosine inverse because some of it's the same, and then I just change the numbers. So I was cheating just a little bit. Okay, vectors. 'Tis time. Speaking of all this real life stuff, I mean, pirates on the sea and very non-cloudy, starry nights, losing their clocks and their, well, they couldn't do the sun if it was nighttime anyway. Anyway, whatevs. Section 6.3, we started writing this down already. Where is it? Oh, there it is. Vectors in the plane. However, to inspire us, I've heard other teachers started doing this, which is kind of sad. It used to be my thing, but that's okay. I'm not bitter anymore. Let's be inspired.
I'm applying for a new film loan. Go by the name of Vector. It's a mathematics represented by an arrow with both direction and magnitude. That's me, because I'm committing crimes with both direction and magnitude. Oh yeah! Check out my new website. Piranha! Oh yes! Fires live piranhas. Ever seen one before? Now you have land back. Doing a demonstration. Oh, ow! It's so difficult sometimes to get land back inside.
Direction and magnitude. Oh yeah. All right, get it in. Chip, chip. Direction and magnitude. Now we're not committing crimes. We're not making piranha guns. But they were mathematically correct to some degree. But wait. What's weird about a vector being a line segment that has direction? Have you guys looked at the picture yet that you've drawn down below and thought about your training in geometry to figure out there's a disconnect right now? Line segment with an arrow at the end. Array! Isn't that what that used to be called? Array, fixed point, and it goes on forever. And how is the forever noted? Arrow. Doesn't. What doesn't it mean? Wait. It does mean line segment. It's a definition. Hold on, pause. This is a vector. And as a vector, it has direction. Which way is this pointing?
That way.
Not. Right? It has direction. But what else does it have? Which means, in some ways, shapes, or forms, an amount, a length. Array didn't have a length. It had a starting point, but it went on forever. So here's the weird thing. I need you guys to go ahead and at the beginning of this vector put a point, because all vectors begin in points, and another point. All vectors end in points. Line segment. A line segment has a beginning, a finite length, or a finite amount, aka a finite magnitude. You need to separate the idea of array from a vector because this is not a ray. Okay? Which is confusing because didn't you write rays like that too? But usually wasn't it like two letters like that? Wait a minute, you never did that. Didn't you always do a double-sided arrow? To help you out, the book is going to show a double-sided arrow, but whenever I do a vector, I'm always going to put a little single arrow because in my head it separates it from array. Doesn't mean you have to use it. And notation-wise, we never call a vector by 2 points. That's improper. We'll just leave that for rays. We'll leave that separate. We do use 2 points sometimes, but we don't really name it that way. I mean, I guess we can, and I guess you might see it every now and then. But I just need, long story short, before we go into this whole section, that is not a ray. This is a line segment, beginning, ending, a line segment with a set length. But what's the arrow for? Direction. It's not saying forever. It's just saying this way. Does that make sense? So in geometry, it says, go, 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 just keep going. But no. Now it's like, no, it's just headed that way. Oh, It's just a pointer. That's all it is. It's just a pointer. You guys have already written down the whole, like, hey, it can be forces. Hey, it can be velocities. One more thing I need you guys to write down. If this starts in a point, I could call this point P, and point P could have, I don't know, some sort of like x1, y1. We'll talk about this more probably on Monday. Point Q could be the ending point, which could have its own little points, which could be another x and another y, so x2, y2. Vector V, see how I used a bold letter right there? But then I used a non-bold letter with an arrow on top. Guess which one's easier for the book when it was typing like its lessons and it was homework problems, and even me and my lessons? Bold letters. Just do Control B, got it, right? No big deal. Or whatever. What is it on a Mac, like Applebee? Huh? A little funny. Coming back, though. Coming back. You're not going to write in bold letters. So what's Section 6.3 and 6.4, how many bold letters do you need? But what do you need to do every time you see it? So right here, I need you to go to him and say, oh, wait, I'm not going to write him thick and bold. I don't want that. I mean, maybe you did, and that's perfect, but don't do that again. It's just going to take too much time. And then I'm going to be like, is that bold? Is that not bold? I don't know. And some of your writing, I don't want to know. So instead, we're just going to put little arrows on top every single time you see a vector. And so I'm going to be reminding you, like, constantly, wait, did you put your arrows? Did you put your vector arrows? You're not going to be bold letters, but when you see it in the book, when you see it on the test, when you see it in the notes, the bold letters are vectors, little lowercase bold letters. It means vector V. We can label this as vector V. But when you're writing it, when you're handwriting it, and when I'm handwriting it, we need to put an arrow on top. It can be a double-sided arrow. Technically, that's fine, or it can be a single-sided arrow. I just like it easier because it's like zoom, zoom. It's faster. I'm lazy. What's mathematical? That's why we like math. It's like, oh, we can just kind of find a formula or a pattern and just use it over and over again. But here's something else that we can say about vectors. No, yeah, let's go ahead and do it. I don't like using it because it does look like array, but yeah, technically you can. You can say from P to Q. But here's what you can write. P would be going the other way. So you could Q if there was down there, but it's not. V is going to be vector PQ, and we're going to learn some more about it. But my question to you is, in the movie Despicable Me, the first one, not the, is there like 3 or 4 now? Is there a 4th one coming? I think I heard there might, anyway. There's some, I don't know what movie it was, I forgot. Oh, Toy Story. There's supposed to be a Toy Story 4 coming, unless that's just a, I don't know. Right? It looks like it. Never mind, not Despicable Me 4. Despicable Me 1. Where else, not stated by name and having nothing to do with the little criminal dude, who was a little lame, but having nothing to do with the little criminal dude, where else were vectors, actual vectors, forces and velocities, really seen in Despicable Me? Okay, I could take that one. Yeah, there were some vectors that work in a rocket going up. That's true. That's true. Some vectors, like the trajectory, and if you guys ever watched Hidden Figures, like how the rocket had to re-enter the Earth's atmosphere and all kinds of cool stuff. Okay, rockets, that's cool, but where else? Maybe. Not the one I was thinking of. Because there's walking, there's motion. There's another scene that has tons of vectors at work. I don't want that, though. Not yet, Joe. Nobody? Lasers, partially with trajectories, etc. That could kind of work. No one's thinking of it?
Are we seeing another video?
Yes. Where a lot of forces were at work. You guys should relate well being in Southern California because you have a lot of these really close to you. And some of you might have season passes to them.
Oh, the Coney Island.
Vectors are forces. Forces acting on you in a roller coaster. Huh.
A roller coaster.
Light bulb. The angle on this thing is not so cool. I know, we should have done the It's So Fluffy one, but coming back. Roller coasters. I want you to look at these two pictures and tell me which one you think, just looking at them quickly, which one you think is more accurate? Which one is more precise? One of them is saying more the ideas, and one of them is being way more mathematically precise. Which one's which? One of them is showing the idea of forces acting on a car and a roller coaster in different parts of like a loop. One of them is showing the idea, and one of them is being precise. The right one is precise. The left one's the idea. How do I know? Do you guys know in the one, what force, if you can read it, but what force the blue arrow is? Gravity. But didn't I just tell you that vectors, the length is important? They don't just go on forever. The length is important. What's true about gravity, no matter where you are in a roller coaster ride? Gravity is always going straight down, and it's constant. What does that mean about the lengths of gravities?
It's the same.
If this picture was perfect, what should be the same?
Yeah, that length.
Oh, this picture is wrong. Why? Because it's saying, well, gravity is longer there and shorter there. That's not true, because vectors, vector notation, the length is important. The actual length is important. Whereas over here, what's true about all my gravities? What's true? They're all the same, like they're supposed to be. Joe?
I mean, the first picture, if the roller coaster is high enough, it kind of be true, because the higher it is...
High enough? Joe, a real roller coaster is not going to be high enough. You're thinking like out in the app. No, we're not going that high. People would need space helmets to go on the roller coaster. Some of you are like, oh. Anyway, shh. I mean, Superman's high, but no. You do lose a little bit of it anyway. So then coming back. This one shows the idea. This one's all right, but this one's more mathematically correct. So let's zoom in on this one, single page. I know, we're almost done with class, but that's okay. You guys realize we have multiple days for this section. I didn't really expect you to do tons this weekend anyway. I think I might go ahead and maybe post in your Google Classroom for this assignment a few of the honors pre-cal videos, because some of you are interested and might want to get started on homework, might have more time this weekend, so I'll let you look ahead a little bit, because I pretty much cover theirs pretty closely to yours. Just do a little bit extra as far as explanation. But these things, oh my goodness, do you see? Not the car, because the car, they're kind of like all starting from the car and branching, like where the forces are in the car. In the car, they're kind of just like all branching from one single initial point. But do you see off to the side how they've kind of all been put, if possible, into triangular patterns? These things are called vector diagrams. And vector diagrams say, let's put it all together in a way that we can put together the two forces that are at work on a car, on a person, on an object, on a rocket, whatever it is. We can put the two forces together and ask ourselves, what's the overall result? Put the two forces together, and what's the overall result? Put the two forces together, and what's the overall result? Put the two forces together, and what's the overall result? Does the word net mean something like overall result? Net profit? In vectors, it'll be called the resultant. See you guys later. Bye. Triangles, they're important. They're going to be used We're going to learn some physics next week. Bye, guys.